Unit 3. Components. Consider the basic components of a pump assembly to be the motor, coupling, bearing, and the pump itself. This part of the program will examine the pump motor as well as typical pump coupling and bearing arrangements. Chapter 1. The purpose of this chapter is to identify and describe main types of motors, starters, enclosures, and motor controls, and to provide basic maintenance and troubleshooting information. This figure shows a motor with a portion of the motor housing removed to show the inside of the motor. The image shows the notch on the shaft that attaches the motor to the pump. A long metal block called a key fits into this notch to allow the shaft to drive the pump. Although pumps can be driven by diesel or gasoline engines, pumps driven by electric motors are commonly used in wastewater treatment plants. There are two general categories of electric motors: DC, or direct current motors, and AC, or alternating current motors. Most, if not all, motors at wastewater treatment plants will be AC motors. DC motors are not frequently used in water, wastewater applications because they are not typically cost-effective in the size range required. However, there are situations where very large or very small DC motors are used at treatment plants. There are a number of different types of alternating current motors: synchronous motors or induction motors, which can be either wound rotor or squirrel cage. Synchronous AC motors require complex control equipment as they use a combination of alternating and direct current. Synchronous AC motors are used for large horsepower sizes, usually above 250 horsepower, 186 kilowatt. The most typical pump motors at wastewater treatment plants will be induction AC motors. Induction motors use only alternating current. The two types of induction motor are the squirrel cage and the wound rotor motor. The squirrel cage motor provides relatively constant speed and is the most common in wastewater applications. The wound rotor motor can be used as a variable speed motor. The wound rotor motor achieves variable speed by way of electrical resistors in the rotor to change the speed of the motor. This method of speed control is not energy efficient and is not normally used. Synchronous motors can be used as variable speed motors. The speed of the motor is controlled by changing the frequency of the AC power to the motor. This method of speed control is called variable frequency drive, VFD. The VFD control replaces the normal starters for the electric motors. VFDs are very efficient. Motor starters. All electric motors, except very small ones such as chemical feed pumps, are equipped with starters. These starters can be either full voltage or reduced voltage. Starters are used because motors draw much more current when they are starting and gaining speed than when they are at full speed. Reduced voltage starters prevent the load from coming on until the amperage is low enough. Throttling the discharge valve reduces the demand for increased current during startup. Throttling of the discharge valve should occur only for a short time during starting of the pump, as extended throttling can cause excessive wear of valve parts. This strategy is sometimes used on large pump motors and is usually a part of the automated startup sequence. If too much current is drawn during startup or at any other time, an overcurrent relay in the starting circuit will shut the motor down. There may also be a heat sensor in the motor that will shut down the motor if the windings overheat. Some large motors have vibration sensors and heat sensors to provide overheat protection to the motor bearings. Motor enclosures. Enclosures for motors used at treatment plants are of various kinds. A common type of enclosure for motors not requiring special protection is an open motor. Open motors have ventilated openings in them to allow air to pass through to remove heat generated when current passes through the windings. Other motors which are used for specific purposes or used in special environments may require special enclosures for safety as well as for protection of the motor. There are a number of locations within the treatment plant that will require special motor enclosures. For example, motors will require special enclosures where they need protection from water or humidity or from explosive gases. The motor enclosure may be referred to as drip-proof, splash-proof, guarded, and so on. The name given to a motor enclosure refers to the kind of protection provided. The drip-proof motor is protected from water drops from above the motor. The splash-proof motor is protected from water drops from the sides as well as from above. Note that both enclosures provide protection from water, but this does not mean that water cannot reach the motor. Even the splash-proof motor can be damaged if it is hosed down. Two types of totally enclosed motors are also common: the TENV, or totally enclosed, non-ventilated motor, and the TEFC, the totally enclosed fan-cooled motor. Totally enclosed motors may also be dust-proof, waterproof, or explosion-proof. An explosion-proof enclosure must be provided on any motor located where dangerous gases might accumulate. Explosion-proof does not mean waterproof, nor does it mean that the motor will not explode. Rather, explosion-proof means that any explosion will be contained within the enclosure, preventing the explosion of gases outside the enclosure. Motor controls. All pump motors in the plant are equipped with some method of control, typically a combination of manual and automatic systems. Manual pump controls can be located at the central control panel, at the pump itself, or at the suction or discharge points of the liquid being pumped. Redundant manual controls may be at the other locations. Even if an automatic system controls normal operation of a pump motor, some method of manual control is always provided. This is because manual pump controls are provided to start or stop the motor in emergencies, to test the motor, or to ensure that power has been locked out before servicing the unit. It is extremely important to lock out power to the motor at the main control panel before servicing a pump. To stress some important safety considerations, let's see what should be done in each of the following situations. You know that the electrician has already locked out the power to the unit because he is installing an ammeter. You are planning to change the impeller on that same pump. What is the first thing you should do? You must put your lock on the motor control center or breaker that provides power for the motor. This means that the lockout will have two locks on it, yours and that of the electrician. Locking the local start-stop button may not prevent an unwanted start. Therefore, if the electrician finishes before you do and removes his lock, neither he nor anyone else can start the pump while you are still working. You have already locked out a pump you are planning to service at the main control panel. What should you do with the local control at the pump? You should use the local control to test that the main panel lockout is effective. To test, turn the pump control to on, or manual. If the pump starts, you've got a problem. You will have to determine why the lockout has not been effective. If the pump does not start, you know the lockout is effective. Be sure to turn the controller to off before beginning any servicing. Joe knows that he has to lock out the pump before he changes the impeller, but he has misplaced his own lock. Joe borrows Fred's lock. What do you think of Joe's decision? While it may seem inconvenient at the time, it is a better idea to get a new lock than to borrow someone else's. To ensure his own safety, Joe should take the time to find his own lock or to get a new one. There should be only one key per lock. The pump motor is usually provided with both manual and automatic controls that start and stop the motor to meet the needs of the system. Control systems for pump applications are generally matched with the requirements of the process. The level sensor is the most commonly used for automatic control of a pump motor in a wastewater treatment plant. Floats are commonly used in sump applications. They are simple and reliable for this purpose. However, they can be troublesome in systems with high grease content. Simple systems using floats generally require very little in the way of control strategy. Some way to switch between hand, auto, and off settings is usually all that is necessary. The more complex the control device, the more complex the control strategy. One type of control strategy is single and multi-loop control, a combination of instruments or control functions that are arranged so that signals pass through each device or function for measurement and control of the process variable. Distributed control systems, DCS, consist of a network of controllers and computers that monitor and control processes throughout the plant. Everything is connected to a central monitoring location where a specific process can be assigned to any one of the control areas of the system. Programmable logic controllers, PLCs, are controllers with multiple inputs and outputs. A PLC consists of an input-output interface, a central processing unit, and memory. PLCs are more reliable than the relay-based systems previously used. These are often used where the sequencing of pumps is required and must occur for the process to function properly. A lot of considerations are involved in the decision to use one specific technology over another. All of the available devices and technologies have their own troubleshooting strategies, and in most cases, an electrician or technician is needed to diagnose the control problem. There are very general steps that can be taken to determine if a problem is mechanical or electrical. Let's see how a typical level sensor works. Level sensor control devices are usually pear-shaped floats, like the one shown here. It is a simple and rugged device. If the water level is low, the float switch hangs vertically. When the liquid level reaches the bottom of the float tilts. The movements of the float switch from vertical to tilted positions open and close a switch inside the float. This controls the pump motor by turning it on or off. This shows the internal workings of a normally open float switch. When the float tilts, mercury in the glass tube flows toward the end of the tube that has two wires attached to it. When the mercury covers the wires, it closes the circuit between the two wires. This is called a normally open switch. If the wires are located so that the mercury flows away from the wires when tilted, the switch is termed a normally closed switch. When performing repair or replacement, it is important to be aware of the potential hazard to the environment posed by mercury. Mercury-containing parts should be disposed of at a facility permitted to handle these wastes. More sophisticated systems than floats are available. In ultrasonic sensors, an ultrasonic transducer emits a series of pulses that are reflected as an echo from the surface of the process material. The same transducer receives the echo, and electronics compensate for temperature. Using time of flight, the electronics convert the signal into distance. Strain gauges are a second type of control system currently in use. A silicon diaphragm is doped to produce a strain gauge bridge. Pressure to one side of the diaphragm causes a resistive imbalance in the bridge. This change is sensed by an electronic network, which produces a DC signal in the range of 4 to 20 milliamps, proportional to the applied pressure. This signal is applied to a controller that has selectable parameters used to open and close relays and thereby control the pumps. A third type of control is the microwave. Microwave technology is used in turbulent, high-temperature, or aggressive material. Microwave technology is similar to ultrasonic devices in that both employ a type of wave technology. In the case of microwaves, at permissible levels, microwaves are bounced off the process material and received by the same transmitter. Output is scaled to a DC signal in the range of 4 to 20 milliamps. Conductive control devices require a liquid that can conduct electricity. This liquid reaches a probe and causes the circuit to close. This kind of device is suited for point measurements only. Variations in process level cause changes in capacitance. Capacitance is measured by a bridge circuit excited by a high-frequency oscillator. The probe is insulated from the vessel and forms one plate of the capacitor. The vessel forms the other. Bubbler level measurement instruments are used throughout the plant process. An open-ended pipe called a bubbler tube or dip tube is connected to an air supply and positioned in the process liquid so that the open end is at a reference level. A constant rate air regulator is used to supply air in the tube with enough pressure to continually bubble air out of the open end. The air pressure in the pipe is equal to the head pressure of the process liquid above the reference level. Sensitive air pressure switches will detect this change and use this information to control pump operation. While this course is dealt mostly with level sensing-based control devices, there are many other control applications.
In many processes, flow through the system must be measured, monitored, adjusted, and calculated.
Optimal dissolved oxygen levels must be maintained in aeration tanks. Recycle pumps can be flow-paced. Service water tanks must be maintained at a certain pressure. Temperature has to be regulated in a heat exchanger. These are all examples of where control systems are used. Motor maintenance. Because of the different kinds of pump motors used, it is particularly important to check the manufacturer's literature for maintenance requirements. If information has been misplaced or lost, the manufacturer should be contacted. Generally, though, there are some basic rules. The motor should be kept clean. Motors should also be kept dry. Moisture harms the insulation on the windings to the point where they may no longer provide the required insulation for the voltage applied to the motor. In addition, moisture on windings tends to absorb acid and alkali fumes, causing damage to both the insulation and the metals. To reduce problems caused by moisture, the most suitable motor enclosure for the existing environment will normally be used. In other cases, a dehumidifying system may be required. Standby motors can be damaged by moisture. To reduce the problem, standby motors should be run at regular intervals to dry up any condensation which has accumulated in the motor. Motors should be causes wear in all moving parts, and lubrication is needed to reduce this friction. It is very important that manufacturers' lubrication instructions are strictly followed. Too much grease or oil should not be added, as this in itself can cause friction and generate heat. Furthermore, an excessive amount of grease may penetrate the motor windings. If this happens, the motor will have to be taken apart and cleaned, either at the factory or by a qualified service representative. It is very important to properly lubricate pump motors to ensure reliable operation. Remember always, turn a pump off before applying lubricant. Motor bearings must be lubricated in strict accordance with manufacturer instructions. These bearings may be greased or oil lubricated. This picture shows a typical grease fitting on a motor. Certain parts of the motor, such as the windings, will be quickly ruined if they are exposed to lubricant. These are oil lubrication parts of a motor bearing. On large motors, there may be three: the filler, the level, and the drain. Oils and greases must not be mixed, since the additives of different oils, when combined, can cause a breakdown of the lubricant. A helpful visual tool to organize lubricants and avoid mixing different types is to assign each lubrication point a color code by type of lubricant. It is also helpful to keep a log of lubrication and other maintenance performed. The motor manufacturer can provide guidance on preventive maintenance procedures. In addition to lubrication, preventive measures would include procedures such as checking connections, performing routine cleaning, taking vibration and temperature measurements, troubleshooting motors. Now that some main routine operational and maintenance concerns have been reviewed, the basic signs that will inform you about motor problems will be discussed. Simple observation can be helpful. For example, is the motor casing hotter than usual? Are there any new or unusual noises, vibrations, or odors? The response to any of these observations should be to shut off the motor to determine the cause of the change. If it is necessary to shut down any machinery, the area supervisor should be notified immediately. Ammeter readings are another main source of information about pump motors. Ammeter readings should be monitored and recorded regularly. Some motors do not have ammeters. In these cases, an electrician should regularly check the current drawn by each of the motors and record that information. If a motor starts drawing more electrical current than normal, problems can be anticipated. Motors are usually protected at the power source where the starters for all plant equipment are located. There are other motor responses or trips that could automatically shut down the motor. These include voltage and amperage changes, high motor temperatures, excessive moisture for submersible pumps, and excessive vibration. On large motors, the motor should not be restarted until the rotor has come to a complete stop. Therefore, there should be a locking system or manual reset to prevent startup of a motor immediately after a trip. Couplings. The purpose of our discussion on pump couplings is to introduce you to the common methods of connecting the motor shaft to the pump itself and their basic maintenance requirements. A coupling is used to connect a motor to a pump shaft. There are many different types of couplings used to form this critical connection. It is also possible to mount the impeller directly onto the motor shaft, as shown in this diagram. This is referred to as a close-coupled pump. These combined pump motor units are referred to as submersible pumps. They are available in a wide range of sizes. The two extremes are shown. Combined pump motor units can be repaired either locally or in-house. These units are usually small, close-coupled pumps, like sub-pumps. The pump coupling is used to transfer power from the motor to the pump. It couples or joins the two shafts together to transfer the rotation from the motor to the impeller. The coupling can accommodate a very small misalignment between the pump and the motor. Care should be taken to minimize this misalignment during initial installation to avoid excessive wear. It is important to remember that any coupling is a device in motion. Consider a 10 centimeter or 4-inch diameter coupling revolving at 1800 RPM. Its outer surface is traveling about 30 kilometers per hour, or 20 miles per hour. All couplings should be protected by safety guards. There are 3 commonly used types of couplings: rigid, flexible, and V-belts. This source will consider the rigid coupling first. Rigid couplings are most often used on vertically mounted pumps. The rigid coupling is usually specially keyed or constructed for joining the coupling to the motor shaft and the pump shaft. There are 2 types of rigid couplings: flanged and split. The flange coupling is used when the motor shaft and the pump shaft to be connected are different sizes. The split rigid coupling, like the one shown here, works well where impeller adjustment is required, such as when the impeller has to be moved towards or away from the motor. The length of this coupling allows for considerable adjustment. A second common type of coupling is the flexible coupling. The flexible coupling provides the ability to compensate for small shaft misalignments, although the shaft should be aligned as closely as possible. The greater the misalignment, the shorter the life of the coupling. Bearing wear and life are also affected by misalignment. So far, besides the close-coupled pump, we have mentioned 2 common types of pump couplings: rigid coupling, flanged and split, and flexible coupling. With both the rigid and the flexible coupling, we have mentioned shaft alignment. Let's see what we mean by this. Alignment of flexible and rigid couplings. Both flexible and rigid couplings must be carefully aligned before they are connected. Misalignment will cause excessive heat and vibration, as well as bearing wear. Usually, shaft misalignment problems will be indicated by excessive noise from the coupling. 3 types of shaft misalignment will be considered: angular misalignment, parallel misalignment, angular and parallel misalignment. Problems are often a combination of angular and parallel misalignment. While different couplings will require different alignment procedures, some general guidelines for aligning flexible and rigid couplings can be given. First, of course, lock out the unit. Place the coupling on each shaft. Arrange the units so that they appear to be aligned. Place shims under the legs of one of the units to raise it. Check the runout, or the difference between the driver and the driven unit, by rotating the shafts by hand. Turn both units so that the maximum runout is on top. Check the units for initial or gross angular alignment. You can use a caliper to measure the distance of one coupling half from the other half. In taking this measurement, be sure that the calipers are at right angles to the faces of the coupling. Measure the distance at several different points around the perimeter of the coupling. There are sensors, like this dial indicator, which measure alignment. Another approach to determining angular alignment uses a tapered wedge. The tapered wedge checks the clearance between the coupling halves at several locations around the coupling. To identify variations in clearance, you simply mark the wedge at point C, where it protrudes from the coupling halves. For information and procedures for more precise measurement of angular alignment, check your manufacturer's literature. The third commonly used type of coupling is the V-belt drive. This method uses belts to connect the pump to the motor. As can be seen from the diagram, a pulley or sheave is mounted on the pump shaft, and another is mounted on the motor shaft. One or more belts are used to connect the 2 sheaves. There are many different configurations or arrangements that can be accommodated with this coupling. The motor can be located either above the pump or beside the pump. The pump and motor shafts must be positioned so that the pulleys can be aligned with the belts in a straight line. The belt tension should be adjusted to the manufacturer's recommendation. Generally, belt tension on new belts will need to be rechecked after a brief initial run. Too much tension shortens belt life and increases stress and wear on the bearings. Too little tension causes loose belts and thus slippage, loss of power, shorter belt life, and wear of the belt sheaves. An advantage of driving a pump with belts is that various speed ratios can be achieved between the motor and the pump. To change the speed ratio between the pump and the motor, it is only necessary to change a pulley. To change the speed ratio between the pump and the motor, it is only necessary to change a pulley. Pulleys can easily be adjusted and aligned. V-belt drive pulleys are commonly known as sheaves. Normally, they are made of cast iron or steel and machined to size. Sheaves can be single-grooved, double-grooved, triple-grooved, or more if required to meet horsepower requirements of the system. It is important to periodically ensure that the sheaves are not becoming worn beyond the manufacturer's specifications. The sludge pump here is coupled to the motor by a V-belt. The protective cage or belt guard must always be in place whenever the pump is running. A finger, loose clothing, a rubber hose, or anything could get caught in the rotating belts, causing a serious accident. V-belt pulleys, maintenance, and repair. Lock out the unit before beginning any maintenance or repair. The belt number found on the belt should be used to reorder belts, as there are many types and manufacturers of V-belts. If there is more than one belt, they must all be replaced at the same time. Purchase and install a match set so that all belts will wear evenly. When installing or replacing V-belts, the motor and belt sheaves must be aligned. The belt must run straight between the two sheaves without any angle. During belt installation, belts should not be forced over the sheaves or over the sides of the grooves. This can damage or even break the belts. Before installing the belts, loosen the motor to bring the sheaves closer together. After the belts are in place, the motor is pulled back and bolted in place. Check the alignment of the motor and the belt sheaves. One method of checking alignment is to use a straight edge to ensure all points touch on the sheaves. With all the belts in their proper groove, the centers are adjusted to take up all the slack until the belts are fairly taut. Replace safety. Adjust the belt until there is about 20 millimeters or 3/4 of an inch of belt movement, or as specified by the manufacturer, from hand pressure at the middle of the belt. After a few days of operation, the belts will seat themselves in the sheave grooves. At this time, you should readjust the belts as required. The belt drive is now properly tensioned, and only occasional readjustment for groove wear will be required. It is important not to adjust the belts too tightly, as this could cause problems like bearing overheating and excessive belt wear. Squealing, glazing, fraying, or other signs of wear and tear are indicators of belt problems. Sheaves should be kept clean. Dust and rust can cause worn sheaves, which in turn can damage the belts. The belts themselves should be kept clean. Dirt, grit, oil, and acids can ruin belts. Shaft. This discussion of shaft bearings will introduce the components and basic maintenance of a typical bearing unit. The bearings are used to support and guide the pump shaft. There are two types of bearings commonly used: ball bearings and sleeve bearings. Sleeve bearings may also be referred to as journal or sliding bearings. Another type of bearing is the roller bearing. The roller bearing is similar to the ball bearing, except it is cylindrical rather than spherical. Regardless of the type of bearing used within a system, the bearings are designed to carry the loads imposed on the shaft. The important word here is designed. The bearings used are matched to the requirements. This means that bearings cannot be replaced with another type unless recommended by the manufacturer. Bearings are interchangeable between manufacturers. One can get a replacement bearing by using the bearing identification number and match it with a replacement bearing. The bearing must, however, be equivalent with respect to the inside diameter, the outside diameter, the thickness, and the material. A bearing equivalent catalog is very useful in ordering replacements. When the ball bearing is looked at in cross-section or taken apart, the inner and outer races are more easily seen. A critical maintenance factor for proper operation of any bearing is proper lubrication. Without proper lubrication, bearings will overheat and seize. The bearings in any unit are in constant motion. It is very important to use the correct type and the correct amount of lubrication. As with motor bearings, the shaft bearing units must be lubricated either by oil or by grease. There are several methods of oil lubrication of the shaft bearing unit. For example, an oil reservoir into which the bearing is partially submerged is common on many pumps. Other approaches are to use ring oilers, drip feeders, oil throwers, or a constant level oiler. Regardless of the particular method of oil lubrication used, there are some basic maintenance procedures. A daily check will ensure that there is proper oiling. As oil collects moisture and dirt, it will discolor. Oil discoloration indicates that the oil should be changed. Overfilling the oil reservoir can be as serious as underfilling it. In all aspects of oil lubrication, manufacturer's recommendations must be followed. Shaft bearings can be grease lubricated. Grease-packed bearings may be sealed or unsealed. Maintenance records will show you what type of bearings are present. It is important to check those records. These maintenance records are easily accessed when kept on file in a computer, such as at this plant. Sealed, grease-packed bearings have a plastic shroud on either side to keep in the grease that was provided at the factory. These are sealed units. Lubrication should not be attempted. If a sealed unit is erroneously greased, grease could work its way into the motor windings. Two fittings should be supplied for grease lubrication. These are shown as the grease fitting, through which grease is added, and the grease relief fitting, or vent plug, through which the old grease is pushed out. When greasing this type of unit, the first step is to remove the vent, or grease relief fitting. Then, pump grease into the grease fitting until fresh grease flows from the vent plug. Be sure to remove the vent plug before adding fresh grease to the bearing. Not doing so can build up enough pressure to cause failure of the bearing. Also remember to replace the vent plug after greasing. Extra caution is required in units with only one fitting in order not to over-lubricate. Some pumps may be supplied with grease cups. For these pumps, new grease is provided by turning the handle down 1 or 2 turns at regular intervals or by screwing down the cap. The cup is filled with lubricant as required. Regardless of whether the bearing unit is lubricated by oil or grease, there are some basic operational checks required regularly. Bearing temperature should be monitored. On larger units, automatic systems may shut down the pumps in case of high bearing temperatures. These systems have temperature sensing devices installed like the one pictured here. Readings of the bearing temperature should be taken monthly. A good recording system of these readings will provide warnings of bearing problems. Any significant increase in temperatures for a given bearing should be investigated. However, a very small gradual increase can be expected as part of the normal aging of equipment. Also, keep in mind that increases in air temperature will also produce an increased bearing temperature. Therefore, record air temperature as well. In addition to routine checks of the temperature of the bearing unit, measurements of vibration near the bearing are also helpful. Portable vibration units can be relatively expensive, and a cost analysis should be done against the cost of a permanent monitoring system. An alternative to having operators take readings on large pumps is to have them taken by an outside vibration analyst. The analyst would not only provide vibration data, but would also provide an analysis of the vibration reading. Shaft bearing seals are associated with the shaft bearing units and are used to keep the lubricant in and moisture and dirt out. A wide variety of bearing seals are manufactured, so it is important to check with your manufacturer's literature before replacing any seals on specific units. These are grease bearing seals. Notice the 2 grease seals. The grease fitting and the grease relief fitting are also labeled. This illustrates an oil lubricated unit. Please note the oil seals. Letters A and B point to the oil seals in this oil lubricated shaft bearing unit. If failure of bearing seals is a problem, the shaft should be inspected. The shaft may be rough or corroded and may have to be reconditioned or sleeved before new seals are installed. Here is a grease lubricated bearing. Grease is added to the bearing through the fitting. On this unit, the grease fitting is located as shown and the relief fitting is located on the other side of the shaft. Here, the bearing cover has been removed to reveal the major components of the bearing. Note the bearing cover, seal, shaft, and bearing grease fitting. Here, the grease seal has been removed and moved to the end of the shaft. Replacement of bearings is complicated, requires special tools, and should only be attempted by a qualified maintenance mechanic. Replacement involves using a bearing puller and requires proper handling, cleaning, inspection, and lubrication, as well as extreme care during replacement to avoid damage to the bearing or the shaft.